have done a lot of playlists for undergraduates or people in graduate school and all that. And I think that once in a while I should also do something that'll be useful for people in junior high school, or what some people call middle school. In Nigeria, I think that's a junior secondary school, or even senior secondary school or high school, depending on where you may be. So, and that's why this playlist is on indices and logarithms. This is a very common topic in mathematics. At I think I remember I must have done this at say third year in junior high school, first year in senior secondary school. That is. So let's move on with the first video, which is about meaning and models of indices. So we start with indices and we talk about the meaning and models of indices. Of course, the outcome we expect from this video, from this lesson, is that learners should understand indices as structure, not just as rules, not just as the rules they've been seeing. So, of course, the rules are there, right? So we're going to talk about the laws of indices in the next video. But the structure is also very important, and that's the foundation of it all. So we start with what indices actually means. What indices mean. So an index or exponent tells us how many times a number, which we can call the base in this case, is multiplied by itself. So an indices is all about how many times a particular number is multiplied by itself. That's all. So if you have a raised power n now, it means you have a times a times a times a times a, and that goes on n different times. So that's a raised power n. A very good example is when you say 3 raised power 4. 3 raised power 4 means 3 times 3 times 3 times 3. That means 3 is multiplying itself 4 times, and that gives 81, of course. In this case now, 3 is said to be the base and 4 is the index or exponent. So I mean, we can use the word index or exponent interchangeably. All right. So, in this case now, the value of 3 raised power 4, where 3 is the base and 4 is the index, the value is 81. So that 81 is called the value. So this shows us that indices represent repeated multiplication. So indices is repeated multiplication. All right. So we then go ahead to talk about the models of indices. What are the models of indices? In this case, we talk about three major models. So the first one is the idea of repeated multiplication model, right? So models of indices, we have first of all repeated multiplication model, which we just talked about. That if you have 5 raised power 7, it means you are multiplying 5 by itself 7 times. So you have 5 times 5 times 5 times 5 times 5 times 7 times 5. That's repeated multiplication model. But of course, from that we can also have an area model. When you multiply a number by itself twice, you get an area. So you have 4 raised power 2, which is 4 times 4. This represents the area of a square with side length 4, basically. And then you have volume model also, which is something like 3 raised power 3. You have 3 times 3 times 3. This represents the volume of a cube with side length 3, right? And the key idea here is that power 2 implies area, power 3 implies volume, but higher volumes imply repeated multiplication beyond physical space, like that. So those are the models of indices. So let's go ahead and talk about the pattern method in dealing with indices. So we can build rules logically from patterns. For instance, if you start with base 2 now. So if you have 2 raised power 4, you know that's 2 times 2 times 2 times 2. That's 2 multiplied by itself 4 times. So 2 times 2, 4. 4 times 2, 8. 8 times 2 gives 16. Now, if we knock off 1, 2, that is subtract 1, 2 from this, you get 2 raised power 3. Or another way to look at it is you divide by 2. So if you divide 2 raised power 4 by 2, you get 2 raised power 3. If you divide 16 by 2, you get 8. Of course, 2 raised power 3 is 8 because 2 times 2 is 4, 4 times 2 is 8. And then divide again by 2. So you have 2 raised power 2, which is the same thing as divide 8 by 2, that's 4. So 2 raised power 2 is equal to 4. Divide by 2 again. You have 2 raised power 2 divided by 2. That is 4. 4 divided by 2 is 2. So if you knock off 1 to here, you have 2 raised power 1. So 2 raised power 1 is equal to 2. But then here you see here that each step down divides by 2. So as the numbers come down like that, we keep dividing by 2. Now what happens next? Let's look at this. Now, how do you find a number raised to power 0? Look, finding a raised to power 0, for instance. So if you consider the pattern, remember where we stopped the last time was that 2 raised to power 1 is equal to 2. What if you divide both sides by 2. So in this case now, dividing both sides by 2 means you have 2 raised power 1 divided by 2. Or, as you can see now, the powers have been dropping. So you have 2 raised power 4, 2 raised power 3, 2 raised power 2. Now you have 2 raised power 1 equals 2. So it means next step after below 1 is 0. So 2 raised power 0 will have to be 2 divided by 2, which is 1. And that is why anything raised power 0 is equal to 1. So generally speaking, any number that is not 0 raised to power 0 gives 1. So in that case, you see that 0 index keeps the pattern consistent. Okay, so then we can move on to negative, and that's where we get the law from, that anything raised to power 0 is always equal to 1. And we have seen the logic, following that repeated, following the pattern method now. So if you go by the negative indices now, we started with 2 raised to power 4 equals 16, 2 raised to power 3, 8, 2 raised to power 2, 4, 2 raised to power 1, 2. Now we've seen why 2 raised to power 0 is 1, because we've been dividing step by step. Now what happens here, if you continue dividing by 2, you have 2 raised to power 0 equals 1. We've seen how that happens. So if we go another step, it means we have 0 minus 1, that's minus 1. So 2 raised to power minus 1 will now have to be 1 divided by 2. That's why 2 raised to power minus 1 is 1 over 2, and 2 raised to power minus 2 is 1 over 4. So we can then discover that a raised to power minus n is equal to 1 over a raised to power n. So that's how that goes. So a raised to power minus n is 1 over a raised to power n, because 2 raised to power minus 2 is 1 over 2 raised to power 2, because 4, in fact, I mean, we can actually do this. We have 2 raised to power minus 1 is frac 1, that's 1 over 2, like that. So that means we can say this is now equal to, so we have this to be 1 over 2 raised to power 1. Then when we come here, this is equal to 1 over 4 now. That's 1 over 2 raised to power 2, right? That's 1 all over 2 raised to power 2. 2 raised to power 2. All right. So if we click out there, we see this is what we have here. So if you keep going, it means that a raised power minus n will be 1 over a raised power n. So that's where negative indices arise. So negative indices represent reciprocals. So negative indices tells you you have a fraction at work right there. Okay. So next, you have this example to simplify 5 raised power minus 3. Of course, from what we know, we can rewrite using that meaning that 5 raised power minus 3 is the same thing as 1 all over 5 raised power 3. So to knock off the minus, you have to introduce the reciprocal. That's 1 over 5 raised power 3. And we know that 5 raised power 3 is 5 times 5 times 5. That's 1. 5 times 5 is 25. 25 times 5 is 125. So 5 raised power minus 3 is 125. So we move on to the idea of fractional indices. Fractional indices now. So we extend pattern in a new direction. What if of course, we already know that 3 raised power 2 is 9, right? So the question now is, what number squared gives 3? So which number will you square to have 3? That's the question we have here. So this is 3 raised power 2 equals 9. So now what squared will give you 3? So, and we discover that that number will have to be 3 raised power half. So that by the time you square, if you by the time you square 3 raised power half, right? You have 3 raised power half. So you square it, and then it gives 3, because 2 cancels 2 right here. And you have 3 raised power 1, which is simply 3. So the number that you will square to get 3 is actually 3 raised to power half, like this. Okay, so that is 3 raised power half now is, and 3 raised power half means square root of 3. All right, because if you square the square root of 3, you get 3. So we can see that a raised power half is equal to the square root of a. More generally, as we are going to see later, a raised power m over n means m is power, so you have a raised power m, then n is root. So that means a raised power m over n is the nth root of a raised power m, like that. Then we have another example. If you talk about fractional indices, imagine that you have 16 raised power half. Of course, raised power half means square root of 16, and square root of 16 is 4. And then you have 8 raised power 2 over 3. That means 8 squared, a cube root of 8 squared. So, and 8 squared is 64. So cube root of 64 is 4. Now, another way to take care of this is this. You have 16 raised power half and 8 raised power 2 over 3. So how do you take care of this? alternatively. So you have 16 raised to power half, and you have 8 raised to power 2 over 3. So what do we do? For 16 raised to power half, of course, you know that is 16 is, you can represent 16 in different ways. You can say it is 4 raised to power 2 raised power half. You can do that. You can also say 2 raised power 4. Anyone you want is fine. You still get the same answer. So you, and then so for this time it means 2 cancels, 2 times half is 1. So you have 4 raised power 1, and that is equal to half. So you have that settled like that. So if you don't want to take that approach, you could also say 16. You have 16 raised power half. That's the same thing as 16 raised power half like this. I know 16 is the same thing as 2 raised power 4. So 2 raised power 4 raised power half. So that means you have 2 raised power 4 times half. 2 here is 1, 2 here is 2. So 2 raised power 2, that's still 4. Same thing. Then for 8 raised power 2 over 3, right? For 8 raised power 2 over 3, 8 raised power 2 over 3, what do? 8 can be written as 2 raised power 3, of course, and that is raised power 2 over 3. So you now come and say 2 raised power 3 times 2 over 3. 3 cancels 3, and you have 2 raised power 2, and that is still 4, like that. Okay? So that is what we have in that case. So we have different approaches to these things. And now let's talk about the power of 10. That's a very special one. Powers of 10. So sometimes to simplify your calculations, you want to find a way of making 10 involved in the story, right? So observe this pattern. 10 raised power 1 is 10. Of course, 10 raised power 0 is 1. 10 raised power, in fact, I think that it is important to add that too, right? 10 raised power 0 is 1 because we already established that anything raised power 0 is equal to 1. So we have that 10 raised to power 0, all right, is equal to 1, like this. So, and with that in place now, we now have this pattern that goes, uh, 10 raised power 0 is 1. 10 raised power 1 is 10. 1 0 is added each time. So 10 raised power 2 is 100. 10 raised power 3 is 1000. So the number of zeros you have with the 1 is determined by the power on top of 10. All right. So that 10 raised power 7 will be 1 with 7 zeros. That's 10 million, right? So 10 raised power 3 is 1000. Now look at this. Each power adds 1 0, just like I said. If you move downward, um, that is, instead of, okay, I mean, we saw 10 raised power 0 already to be 1, right? So if you have to move downward, it means you're dividing by 10. So that means 10 raised power 0 is 1. That means 10, the next level below 1 will be 10 raised power minus 1. That means 1 divided by 10, which is 0.1. Okay. Should I show that? I think it's important, just for to be detailed, right? So we have this to be dfrac, all right, dfrac 1 divided by 10, and that is equal to this. So on the other hand too, we have we have 1 divided by 10 raised power 2, 1 divided by 10 raised power 2, okay, which is 1 divided by 100, like that, and that's all we get. So you see now, okay, something is not right here. What did I do wrong? Frac, okay, 10 raised to power 2. Okay, I think that's it. 10 raised to power 2. So that's what we have now. Okay, double equality. I have to remove 1. Yep. So that's it. Yes, 10 raised power minus 2 now is 1 over 10 raised power 2, and that is equal to 1 over 100, which is 0.01. So powers of 10 shift the decimal point. So if you have powers of 10, you are shifting decimal points, and that's what powers of 10 do. So powers of 10, if you have positive powers of 10, they add zeros. If you have negative powers, if you have positive powers of 10, they add zeros. If you have negative powers, they shift decimal point to the right. If you have negative powers of 10, they shift decimal points to the left. Okay, yeah, let's just go on and we'll see a practical application of this when we talk about standard form, or what we call scientific notation. So any number can be written as a times 10 raised to power n, where a lies between 1 and 10. A can be a start from 1, but it doesn't get to 10. So it can be from 1 to 9.9999 something, but never 10. So it can be anything from 1 to 9.999999, but it doesn't get to 10. So an example, you have 4,500. 4,500 is 4.5 times 10 raised to power 3. Why? Because if you have 4,500, you have 4,500. So here now you can't, if there's no decimal, you can imagine that the decimal point is here. So you move on till you get to a number between, you get an A that is to, from 1 to a number before 10, any number before 10, right? So in this case now, yeah, this is 4,500. It's bigger than 10. 450. If you move the decimal here, you have 450.0. That's bigger than 10. You count the number of steps. That's one. Okay, well, I can just leave that first. Then move the second one. You have 45, which is still bigger than 10. Then you move again. You now have 4.5, which is less than 10, right? It's bigger than 1, but less than 10. So how many steps have you moved? One, two, three. So how do you write that? You have 4.5 times 10. Because you moved to the left, so it's going to be negative. So you have 4.5 times 10 raised to power minus 3. That's what that is. Sorry, because you moved to the left rather, okay? Because you moved to the left, it's going to be positive. You have 4.5 times 10 raised to power 3. That's how, so 4,500 in standard form or in scientific notation is 4.5 times 10 raised to power 3. So on the other hand, if you have 0.0032, see what happens there. 0.0032. For 0.0032, right? 0.0032. So the decimal point is right here. Okay, so again, 0.0032. Don't forget you need a number A that is from 1, but it doesn't get to 10, right? So you can see 0.0032. 0.0032 is less than 1, and you cannot have anything less than 1. Okay, so in this case now you have, so to get something less than 1, in this case you move to the right. Okay, move to the right one step. That's 0.032. It's still not 1 or bigger than 1. Then you move again. The second step, that you have 0.32, which is still not up to 1. Then you have to move one more step. So by the time you move one more step, you have 3.2, which is bigger than 1. Of course, if it was 1, it's fine too, but it's bigger than 1, so we are good. So about if you move one step further, it's bigger than 10. So 3.2 is what you need. Now the question is, because you're moving to the right, it has to be negative, right? Because the number itself is smaller than 1. Okay, so in this case now you have 3.2 times 10 raised to power. How many steps did you move to the right? That's 3 steps. So because you move 3 steps to the right, you have minus 3. Steps to the left is positive, steps to the right is negative, like that. Okay, so 0.0032 is the 3.2 times 10 raised to power minus 3. And this is what we call the standard form, or the scientific notation for that number. Okay, so then let's look at some equivalent forms. That is, if you want to rewrite in index notation, right? Um, Imagine all these examples, for instance. Okay, let me just expand as much as I can so I just move step by step. Okay, equivalent forms now, rewriting in index notation. Example, you have 7 times 7 times 7 times 7. That's 7 raised to power 4 easily. Then x times y times y times y. That's x appears twice, y 3 times. So you have x raised to power 2, y raised to power 3 easily. Then another one, you have this that you have 3 raised to power 2 multiplied by 3 raised to power 4. So 3 raised to power 2 means 3 times 3. 3 raised to power 4 is 3 times 3 times 3 times 3. If you do everything together, you have 3 in 6 places. So that'll be 1, 2, 3, 4, 5, 6. So all of this is just 3 raised to power 6 because there's 6 threes. So generally speaking, if you have a raised to power m times a raised to power n, that will simply be a raised to power m plus n, like that. Because from what we've seen now, 3 raised to power 2 times 3 raised to power 4, 3 raised to power 2 into 3 raised to power 4 simply means you have 3 times 3 on one hand multiplied by 3 times 3 times 3 times 3, right? So, and that is 3 times 3 times 3 times 3 times 3 times 3. So generally we have 3 raised to power 6. But instead of going this long distance, because we already know that that is the answer it gives. So we can say 3 raised to power 2 into 3 raised to power 4 can easily be expressed as 3 raised to power 2 plus, okay, if you like, just for the sake of it, 3 raised to power 2 times 3 raised to power 4. That's simply the same thing as 3 raised to power 2 plus 4. That's 3 raised to power 6. So instead of having to do this elaborate process. So, and from there, we now see that we can have a general rule for indices. Of course, we're going to see the rules very soon. That if you have a raised to power m multiplied by a raised to power n, it is simply the same thing as a raised to power m plus n. Okay, we're going to see all the rules in the next video. So now we are just trying to talk about the meaning and the models of indices. So generally, a raised by n times a raised by n is a raised by m plus n. So imagine these two. Imagine that you have 5 raised by 7 divided by 5 raised by 3. The answer is simply 5 raised by 4. And that tells us that if you have a raised by m divided by a raised by n, that will give you a raised by m minus n. Of course, what are we talking about? 5 raised by 7 divided by 5 raised to power 4. Okay, so 5 raised by 7 divided by 5 raised to power 4. That's 5 times 5 times 5 times 5 times 5 times 5 times 5. 1, 2, 3, 4, 5, 6, 7. Divided by 4, 5 raised to power 4. That's 5 times 5 times 5 times 5. Okay, so uh, this cancels this cancels this cancels this, and this cancels this. Okay, at the end of the day, we have 5 times 5 times 5 left, which is simply 5 raised to power 3. Okay, and since we've seen that there's no point wasting time next time. If you have 5 raised to power 7 divided by 5 raised to power 4, that's simply 5 raised to power 7 minus 4, which is 5 raised to power 3. And that's it. Generally speaking, then we can say that if you have a raised to power m divided by a raised to power n, that's the same thing as a raised to power m divided by a raised to power n, and that is simply a raised to power m minus n, like that. So that's another rule we are going to come across when we get to the second video. So in all, we can summarize that indices describe repeated multiplication, pattern continuation, reciprocal structure, root structure, decimal shifting when you talk about base 10, like that. And the key forms of all this we can see to be the following, that a raised power n talks about repeated multiplication n times. Then you have a raised power 0, that's 1. Anything raised power 0 is 1. Then we've seen that a raised power minus n is 1 over a raised power n. All right. Then we've seen that a raised power m over n is equal to the nth root of the mth power of a. That's the nth root of a raised power m. And then 10 raised power n talks about a decimal shift. If n is positive, you have a decimal shift. The decimal will shift to the if the power is positive, right, the decimal will shift to the left, right? Mm. If n is positive, right, it will add, the decimal will shift to the right. If the decimal is negative, the power will shift to the left, something like that. So indices are logical pattern extensions, not isolated rules. So it's not just about the rules. There's a particular pattern everything is following. So we have 20 questions here. Maybe I can show them in tens. Okay. Yeah. So top 10. Simplify your or rewrite each expression. Show full working. 3 raised by 5. That's 3 times 3 times 3 times 3 times 3. That's 3 times 3, 9. 9 times 3, 27. 27 times 3, 81. 81 times 3, 243. 7 squared is 7 times 7, simply 49. Then this is 2 raised by 4 times 2 raised by 3. Of course, this is just 2 raised by 7, which is 128. Then 5 raised by 6 divided by 5 raised by 2. That'll be 5 raised by 6 minus 2. That's 5 raised by 4. That's 25 times 25. That's 625, I believe. 4 raised by 0 is 1. Anything raised by 0 is 1. 9 raised by minus 1 is 1 over 9. 2 raised by minus 3 is 1 over 2 raised by 3, which is 1 over 8. 6 raised by 5 over 6 raised by 5. That is, they are the same, so that's 1. Or if you like, you can say 6 raised by 5 minus 5. That's 6 raised by 0, which is also 1. Anyhow you want it. 10 raised power 4 is 1, 0, 0, 0, 0. Because we have power 4, so there will be 4 zeros with the 1. And 10 raised power minus 3, of course, that will be 0.001, right? So 10 raised power minus 3, 10 raised power minus 3, 10 raised power minus 3 is 0.001. So that for you to get that back, now it will be 1, 2, 3. Because this is where it's after 1 that it becomes, uh, you know, minor, 1 like that. So you move like that to the right. Okay. So again, we have, okay, the next 20, the next 10, we can show the next 10, and that's 11 to 20. Hope that we don't be too much. Okay, I think it's fine. Okay, maybe I'll show the next 5 so that we can see it better. So from 11 to this. Yeah, here now you have x times x times x times x times y times y. This is x raised power 4 times y raised power 2. That'll be x squared y x4 y2 x raised power 4 y raised power 2. We write an index. This is a times a times 3a is 3b, so a cube b cube. Simply simplify this. That's 3 raised power 7, right? Simplify 8 raised power half. That's that'll be 8. If you like, you can say 2 raised power 3 times raised power half. That'll be 2 raised power 3 over 2. All right, 2 raised power 3 over 2. That'll be square root of 2 raised power 3, Or you can also split it as 2 raised power 2 times 2 raised power half. So that you get 2 roots 2. I mean, maybe I should do that. 8 raised power half, right? 8, you have 8 raised power half. That's the same thing as 4 times 2 raised power half. That means you have 2 raised power 2 times 2 raised power 1 raised power half. As you're going to see later, we can actually split this up as 2 raised power 2 raised power half times 2 raised power 1 raised power half. So 2 cancels 2 here. So we have 2. And for this one, it's just 2 raised power half. Okay, that's just 2 raised power half. And then we can leave it as that square root, right? That will just be 2 root 2. So that's all we can do with that, like that. And then okay, yeah, you can complete all these other ones. Um so 15 to 20. Now 27 raised by 1 over 3. That is cube root of 27, which is simply 3, or 2 raised by 3 raised by 3 times 1 over 3. That's 3. Then simplify. So try your hands on this. Okay, for in standard form now you have 1, 2, 3, 4. That's 8.1 times 10 raised by minus 4. Then for this 2 times 2 raised by 6 times 2 raised by 3 over 2 raised by 4. That's 6 plus 3, 9. So 2 raised by 9 over 2 raised by 5. That's 2 raised by 9 minus 5. That's 2 raised by minus 4 rather. That's 2 raised by 5, which is 32. And then to simplify this, you have 5 raised by 2 raised by 3. That's 5 raised by 6. And that's it. So with this, I come to the end of this interesting video on the meaning and models of indices. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. And if you're preparing for an exam like CBSE, IGCSE, West African Secondary School Certificate Exam, Nigeria Economic Council, Nigeria Examination Council Senior Certificate Exam, SAT in the US and other parts of the world, this is a very useful video for you. So let me know how helpful this is. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you so much for doing that. If you haven't subscribed, go ahead and subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel. That comes with some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to this great content I have going on here. Till I come your way again, keep doing maths right. Bye.